Hi everyone, Mr. Lee here. In this video I'm going to go over the FRQ for our first experimental design problem. Alright, to start off, this problem talks about a toy, bouncy ball toy that has a claim that it doesn't matter where you drop it from, no matter what height, it'll always bounce back up to that same height. Now in this experimental design we have a student that's highly skeptical. They say, I don't think so. Their hypothesis states that for a low impact, I believe, it'll be perfect, 100% elastic. Okay, but they said for high impact stuff, it'll be less than 100% elastic. Okay, so what this means here is that the student thinks that if you drop it from a low height, pew, boop, it'll bounce back up to the same height. But they say that the student thinks that if you drop from a higher height, pew, it won't go up as high. So this will go up to the same height and this won't. All right, let me do a better job of sketching out the two. So they say for a low height, pew, right, it bounces up, goes back up to the same height. They say for a high impact one, it won't go back up as high. Okay, that's the student's prediction. All right, so when you approach this, what I like to usually do is I like to look at the scenario and I like to think about what unit that we are on. So usually for anything that deals with collisions, we have momentum stuff, okay, and anything where we are dropping things, okay, anything that we are dropping things, we have energy things. Okay. Now for collisions, this is a little side note. You can approach this problem using the conservation of momentum, but it's a little bit more tricky. Okay. Usually with collisions, you have like two objects colliding against each other. Okay, you have two objects that collide against each other, and with dropping and energy, I think this is a little bit easier to do, as you can see with our equations. All right, so we have our topics here, and we just kind of take a look at the scenario. All right, so when we are dropping these objects, we have the different forms of energy. So the first one is the gravitational potential. We have mgh, and when that is starting to move, that gravitational potential turns into kinetic energy, K equals 1/2 mv squared. All right, and within these two equations, we can see what equipment that we can use. Now, hopefully you have that chart of the equipment that you should use for the experimental design things, but for M, we can use what we call a scale. G is a constant. Okay, so G is just 10 meters per second squared, so we don't have to worry about that. And H, because we are measuring the height, we can use a meter stick. Right, and over on the other side, we still have M for scale, and we have V, and for V we can use a speedometer. Okay, we can use a motion detector, or we can use a photo gate. Now between these three, let me just give you a little bit of clarification. A speedometer and a motion detector, well, let's do a motion detector. So a motion detector is good for when a object moves towards / away from the detector, right? Kind of like the police, they use a speed gun, okay, to see how fast you're going, or like a baseball, when a pitcher pitches the ball, they can see how fast it's going, right? Now a photo gate is useful for when objects move through the gate. Now, because of the distinction between the two, I want to focus on the photo gate here for the setup. Now, I can tell you that you can use both, but I think the photo gate method is a little bit easier. All right, so we have two methods. We have either the potential energy method or the kinetic energy method. So I'm going to go over both methods first, and then we can go from there. So with the potential energy method, you will release the ball, right? You will determine your initial height, and when it bounces back up, we can see what the final height is. Right, and the reason why we know like these are the two things that we have to measure is because in the equation we have mgh initial is equal to mgh final. And so here what the student is saying is that, well, the mass of the objects aren't changing, right? The acceleration due to gravity doesn't change. So the only thing that we can use as evidence to either support this toy's claim or go against the toy's claim is the bouncing height. So the procedures will follow as such. Okay, you can either get the initial height or the final, or you can get the initial height and the final height of the ball's bounce. And I'll show you how to write that out. The other method is the kinetic energy method. Now this one's a little bit trickier. I'm going to zoom in here so we can do a little bit more of a detailed drawing. So remember, for a ball that is dropping, right? Pew! Okay, we want to get the kinetic energy when it's at the greatest kinetic energy, and that is right before it hits the ground. So this is KE initial max, right? And then when it bounces off, okay, right as it's leaving, boop, right here as it's leaving, this is the kinetic energy final max. So we want to see how fast it's hitting the floor and how fast it's leaving the floor, and that way we can compare the two kinetic energies. Okay, mv squared is equal to 1/2 mv final squared. We can get some stuff out. 1/2 cancels out, mass cancels out, and so what we're looking at here is the impact velocity, okay, versus the launch velocity. LAUNCH. There we go, the launch velocity. All right, now the best way to do this is to put a photogate. Okay, to put a photogate, and I'll do the photogate in a different color. Let's do it in green. Usually these are black, but we'll put a photogate. Why is that so thick? I don't want that. We want a photogate like so that the ball can go through this gate, right? So the ball will go through this gate and it'll measure how fast it went through the gate, and we'll have another, well, it's the same photogate, right? But when the ball goes through the photogate again, okay, when the ball goes through the photogate again, it'll pick up how fast it's leaving the floor. Okay, so it'll pick the ball's velocity as it goes through the gate, and it'll pick up the velocity as the ball leaves the gate. Okay, so there are two instances of velocity there. Now, another way that you can do the speedometer, you can't put a speedometer here on the floor because the ball will hit the speedometer, okay, or the motion detector. And so what you can do is you can put the motion detector above the ball. Okay, so you can put the motion detector above the ball. So the reason why I'm drawing circles like that is because motion detector is a lot like sonar. Okay, and that's like the sonar symbol of like an echo kind of thing. So you can put the motion detector above the ball, and when you get the graph from the motion detector, you'll get something really, really cool. So the graph of the motion detector will give us something like a velocity time graph. Initially, when we first drop the ball, the velocity will be 0, okay, and it'll show us that the ball goes up, okay, and right here at its peak, this is when it hits floor. Okay, that's how fast it hits the floor. And then when it goes back up, so it speeds up, and then it'll, how will it do this? It'll reach 0 again, and we start off with the same velocity, but it'll decrease like so? I think it'll be like this. Positive velocity, negative acceleration. Yeah, so the graph will look something like this. And the reason why I know this, here, this part of the graph is the launch. Is when you first drop the ball, okay, it takes a while for it to speed up, and so that's what this upward curve motion tells us. It's gonna remain motionless for a little bit, and it's picking up its speed, it goes whoop, right? For here, the launch, one might think that it'll look like this, right, the inverse, but that's not so, because if we take a look at this graph here, and what it tells us is that when it's leaving the floor, okay, it has a super fast velocity, which is up there, but as it's rising, the velocity will decrease, okay, it's slowing down, and so we get this effect. And notice here, it takes a while, so I'm going to highlight this portion, right? It takes a while for it to pick up its velocity, and here it takes a little bit for it to slow down. Okay, so it's like a mirror effect. All right, so anyways, that's the kinetic energy version. if we see that the two velocities, if they're not the same, and that pivot point, that important point, I'm going to zoom in again, it's right here. Okay, if these two values are not the same right there, then we know that something went wrong. Okay, now personally, when I first approached this problem, I liked the potential energy method, and then I'll show you the answer key for both methods so that you can better assess, how to solve it if you are using either way. Okay, so I'm going to do the potential energy method first. Now, here's my little clue. Keep it short, okay? Keep it maybe within 3 to 5 steps. So what you want to do is you actually want to be writing out the equation, and you want to use that equation as a template. All right, so we have mgh initial is equal to mgh final. All right, so what we need to do is we need to determine the actual things that are going to help us to prove this hypothesis or not. So if we take a look up here, we've said the only thing that matters is your initial height and your final height. Okay, and so my steps will reflect that. So step 1, you want to measure the initial drop height. All right, so boom. 2, with a meter stick. I almost forgot. Okay, so you want to make sure always reference the equipment and the variable that you are using. Okay, step 2, we want to somehow find a way to measure the final drop height. So you can say drop the ball, and then see how high the ball bounces, and measure that height. And so if you were to imagine this in the classroom, right, we would have like a group of students, like they're all eyeing it up, and they're trying to find the best height that it bounces up to. Okay, so what we're doing here is we're finding the final height, okay, with a meter stick. Now the way that we do this in class is we actually tape the meter stick against a wall. Okay, so you can imagine that we have like meter sticks against the wall, and so that we can eyeball it a little bit easier. But the most important part is the last part. So step 3, you want to do a couple of things. You want to repeat the above steps, and I would say about 10 times. Okay, and that is to reduce variance and error by determining the average. Okay, so step 2, it's not as accurate as possible, but step 3, what step 3 does is we are trying to get rid of the percent error by repeating it about 10 times. Now this is just a good number to always reference. Repeat 10 times, and that just in our experimental world, the more we repeat, so technically we want to repeat this like infinite times, right? We actually want infinity, but we can't do infinity within a classroom setting, so we just say 10 times so that we can find the average height, right? And my step 4 would be repeat steps 1 through 3 from different drop heights. Now this one is important. I'm going to start this one. I'm going to highlight this one. The reason why we want this step, okay, is because we want a changing variable. This is the changing variable. This is what we are actually doing, and this is what makes it a experiment. And that is because the student actually said from a low drop, okay, from a low drop it's going to look elastic, and from a high drop it's not elastic. Okay, and so step 4 is mucho important. Okay, now the steps will be very similar for the velocity method. Okay, except if we take a look at the kinematic or the equations for kinetic energy. Okay, once again, get rid of all the constants. Don't need that, don't need that, don't need that, don't need that. I would repeat, or I would do the steps this way, right? So step 1, place a photo gate near the floor to measure, I guess, initial velocity, right? Initial impact velocity. Boom. All right, so see what I do here. Here's my steps. Tool. Okay, I'm going to highlight this. I mentioned the tool, and I also mentioned the variable that the tool will measure. Okay. Let's see. Place foot again near the floor to measure initial velocity / final launch velocity. Okay. So that gives me v initial and v final. All right. And then step 2. This is where the actual steps come in. Drop the ball in order to measure the different velocities. Okay. Oh boy. Step 3 will be repeat above steps at least 10 times. And then step 4 is to repeat steps 1 through 3 from different heights. Okay, so one thing that you'll notice is that my step 3 and my step 4 are the same for both procedures, and my method of approaching this is the same, right? You gotta get the tools, and you have to determine the variable that will help with the tools. All right. So for part B has us looking at how you would represent the data in a graph or a table. So I'm going to show you both. I'm going to just show you from the height method. Because the velocity method is the same. We just have to change the variables. Okay. So let's do height initial versus height final. Okay. So we say that from a low height, the drop height and the bounce back up height, it should be the same. So we can say like 0.1 meters, it should be 0.1 meters, okay? 0.2 meters will be 0.2 meters, okay? So this is still very close to the floor, right? This is about 30 centimeters. And then things start to go awry, right? Let's say from a slightly higher height, right? And so we can like continue this, or we can say like, oh, so starting from 0.4 meters, it's gonna actually be 0.35. Ooh, okay, we're getting a little bit spicy. And a half of a meter, ooh, I don't know, it's gonna be like 0.4. All right, so we are showing the graders. Yeah, I get the situation. Okay, I'm showing us what it could be. All right, so it's not equal. So the important thing is that low heights, they were equal, and for the bigger heights, they're not equal. Okay, that shows us that it is not elastic. And for the velocity one, okay, it could be the same idea, except instead for meters, you could have like meters per second, and just replace the variables. Now, graphically, if it's a 1-to-1 ratio, we can say that your initial height versus your final height, right? Initial height, final height, it should be linear. Now, things start to go awry when it doesn't become linear. So I want to break this up into 2 groups. This is perfectly elastic, right? As initial height goes up, final height goes up, right? It's perfectly linear, but then things start to get a little funky here. And that's when your initial height goes up, but your final height doesn't go up as much. So this is another way that you can represent it. And of course, we can also just use the velocity as well. All right, so that's for B. Okay, now for part C. The thing I want to highlight for part C is that something violated the laws of physics. Now, what violation means is that if this were happening in real life, you'd be like, something's weird. Like, it just got into Twilight Zone territory. So we know that if we drop a ball, boom, if it bounces back up to the same height, okay, that's fine. Okay, that happens. We drop a ball, it doesn't bounce back up to the same height. Yeah, sure, that happens. Now this is what's weird. If we drop a ball, and then it goes up super high. That's weird. That is super weird. That is a strict violation of everything that we hold dear in our universe. This is a strict violation. Something went terribly wrong. So step C says, student carries out experiment analysis described in parts A and B. The student immediately concludes that something went wrong. Okay, because the graph or table shows behavior that is elastic for low-speed collisions, but appears to violate a basic principle for high-speed collisions. So this is a strict violation. Okay, and so they're asking for a table. So the idea will be the same, right? HO, HF, so that could be VO, VF, right? So we can say 0.1, good, 0.1, good, 0.2, good, 0.2, good. And then like, as we get higher, so I'm going to say like 0.7, 1.0, what? 0.8, 1.5, what? Okay, like something went terribly wrong, right? It's bouncing back up higher. So this is good. This is no good, right? This is a strict violation. And so that's what they mean for C1. And yeah, so that's a violation. And what you can say here is that this is a violation of the conservation of energy. Okay, it's a violation of the conservation of energy. So this part here shows us work was done, because somehow this ball gained energy. All right. Okay, so that's just my quick run through of this problem. Hopefully you were able to identify the correct equipment, the correct variables for that equipment, and you got a sense of how to write out the procedures. Yeah, and in other words, tomorrow when we do our next FRQ, a couple of things to remember: keep the list short, find the equations, and just go from there. Right? All right. I'll see you next time. Bye bye.